some forces is going to be equal to mass times acceleration. That's our template. So I got my 4 equations. I have my coordinate systems set up here for mass 1 and for mass 2. All right. Somebody give me one of them. Take chances. Make mistakes.
I 1/2 is gonna be.
Perfect. Wait, say it again. I 1/2.
The tension force minus the weight, 1 sine theta 1. Equals mass times acceleration.
One small mistake. Now, it's something that I've seen this written type of thing written. If I was asking for equations of motion, I would take off something for this. It's also possible that as you're working through it, you would correct it without thinking about it. But from a notation point of view, there is one small notation issue.
Is it a plus?
No, it should be minus because the tension and W1 sine theta 1 are in opposite directions, so one of them is positive, one of them is negative. That's not the problem. Nothing wrong with the left-hand side. Therefore, there's something wrong with the right-hand side. The equal sign is okay also, so there we go. Now we're to the right-hand side.
It should be mass 1.
There we go, mass 1.
Okay.
There are 2 masses. All right. A new voice, someone with a new equation here.
That would be y1 minus w1 cosine theta 1. Would that one also equal m1a?
So close.
Just M1, or is it?
I
So
like
it
one A better
cancels
than just
out.
in one. Sorry?
The acceleration cancels out.
Wording. It cancels
Or
out
is it-
implies that there's something that's gonna cancel it out.
Is it m0?
There we go. Yeah, it's 0.
Okay.
I assume, James, that's what you meant.
Not exactly, but yeah.
Oh, okay,
I would have gotten it while I was doing the equations.
okay. Yeah, it is equal to 0. Technically, that's 1 times 0, as Jacob said at the end, which ultimately is 0. All right, 2 equations to go. So let me randomly pick someone. Ariana. Give it a shot. Looking at this down here.
FT minus O2.
You said FT minus,
Right.
you're looking for things that are in opposite directions. Those are not completely opposite. These are, you're looking down here. So it's FT would be minus the one that's going in the opposite direction here.
So O2 sine.
Sine theta 2. All right, the only other correction I would make is I said down the ramp was positive in this case over here, so it'd be the flip around. So W2 sine theta 2 minus the tension. All right,
Mass. Acceleration.
times what?
Acceleration.
Yeah, okay. There we go. Are these accelerations the same? Will both masses move together? Got one nod, bunch of stairs. One, I'm not quite sure what that was, Ian.
I would assume so, but.
Okay. It is an ideal rope, it doesn't stretch, so it's not like one can start moving without the other one moving too, they're gonna move together. So the accelerations are indeed the same. That was indicated over here by the fact that I used the same letter A for both of them. So yes, it's just M2A. And one to go.
Would it be weight 2 cosine theta 2 minus y2 equals 0?
It would be. And now substitution. I have formula for weights. So my weights will. So this becomes Ft minus M1G sine theta 1 is equal to M1A. This one right here, I typically I'll make the substitution and I bring it over at the same time, so I have Y equals M1G cosine theta 1. Can be done in 2 steps, but which I think I did last time, that should be Y1. Then I have M2G sine theta 2 minus Ft is equal to M2A. And M2G cosine theta 2 equals Y2. Because friction's not involved, the J hat problem, the equations are not gonna have any impact here. So I'm basically looking at these 2 equations here. And I'm just gonna add them. Because the tangents are gonna cancel out. This is the advantage of having A be down the ramp for one of them and up the ramp for the other. So when I add the 2 equations together, my tensions are gonna cancel out because I got a positive and a negative one. So I have M2G sine theta 2 minus M1G sine theta 1 is equal to M1A plus M2A. And I'm solving for acceleration, so I have acceleration on one side, I can factor it out, and then divide, so I have M2G sine theta 2 minus M1G sine theta 1 divided by M1 plus M2 is equal to A. So now I have an equation for straight plug and chug. And what numbers I use, M, should be a 2 there. So I have 8 times 9.8 times the sine of 30 degrees minus 6 times 9.8 times the sine of 57 degrees divided by 8 plus 6. Roughly top is, the numerator on the top, and that is 30 degrees, not 38. 38 degrees. So it's gonna be roughly 40 minus 48 on top. And 14. Bottom one I'm feeling confident with, 14. Take a step and darken this one. What is it?
$39.2 and $49.3.
49.3.
Yep, same thing.
And so this comes down to negative 10.1 over 14. $49.3? You got two people with that? Okay. All right, and so it's roughly 5/7, so somewhere around negative 0.7.
Negative 0.72
Units?
meters per second squared.
All right, so we have a negative acceleration here, but we did not bring friction into it, so this cannot mean that it's not moving. What does this mean? What does the negative acceleration mean? There we go. What does the negative acceleration mean this time?
Doesn't they'll both go up the ramp?
Not that they both go up the ramp.
It's that M2 goes up and M1 goes down.
Right, which is what Brandon said to start with. If only we had just believed him, we could have saved some time. But it does tell us that, I know that this is gonna slide that way, that's gonna slide this way. So now, we can identify the direction of friction, because we know which way it wants to move. So if we bring friction into it, and we'll see what kind of stunning visual effects I can pull off of this one. Say, well, arm shows up on the dirty board. So friction, when we add that into it, be acting this way. And if there's friction here, it will be acting this way. So a couple of years ago, I gave a problem similar to this. I did not give one of the angles. I gave one of them, did not give the other, gave the masses, and I said, what does that angle need to be in order for it to be in equilibrium? In other words, equilibrium, acceleration is 0. So you would end up solving for theta 1 or theta 2, whichever one it didn't give. And then I cut that angle in half, or double, I think cut it in half. And so it would be clear which way the thing was going to move. And then threw friction into it. And I broke it down bit by bit. The first one was find the equilibrium point, and then I threw friction in. Now, if I've got friction acting on both of these masses, from a calculation point of view, if I throw friction into both of these masses, it becomes really difficult to tell how much friction is acting on one versus the other. All I can know is what the total friction is. And so let's go ahead and artificially just sort of give one side friction and the other side will keep frictionless. So let's make this frictionless over here. And over here, let's say mu is equal to mu sub s is 0.1, mu sub k is 0.05. So F2 we don't have to worry about because I made it frictionless. So we do have F1 going this way, F1 going this way. And, oh. Do I want to change my convention? Do I want to, because I know now it's going, if it accelerates, it's going to go, mass 1 is going to go down the ramp, mass 2 is going to go up the ramp. Do I want to switch my convention or keep it the same? It makes it sound like there's a right or wrong answer. It all depends on how you want to interpret what we end up with in the end. Anyone with emotional scars from negative acceleration? Is that Amy, I saw the corner of my eye, I thought. Yep. All right. So what we're going to do is, since I know acceleration is that way, let's switch our directions around. So let's make down the ramp I1 hat, perpendicular J1 hat, and then over here, we'll keep J's where it is, so I2 hat. Now I could have just started sticking negative signs in there, but may as well start with a cleaner slate. So I now have, there we go, I now have, that is my positive direction, those are my positive directions, and over here, those are my positive directions. All right, so, got the 4 equations of motion. This time I got friction added to one of them. Let's see, let's randomly pick somebody. Amaje, give me one of the equations. Which one are you're doing? Y1, so you're doing here, okay. So Y1. Cosine theta 1. You said M0? Yep. Or we can just write 0. Technically M1 0, but still 0. All right, got one down. Let's see, who have I not heard much today from? I think Amy is, it's time.
Will be FT minus W1 sin theta 1.
The only difference is we've switched down is positive now, down the ramp.
So FT plus L to 3.
All right, so the easier way of doing this, we're doing this I1 equation apparently, from what you had said. So what are all the forces in the positive direction? In the positive I hat direction?
Will be the cosine.
Looking I hat down the ramp, along this line. What are all the forces in the positive direction?
Friction. Will be friction.
Friction's going up the ramp, so that's in the negative direction.
Sin theta.
so you have W1 sine theta 1. And now the one's in the negative direction, which you've mentioned already, but let's make it official.
Friction.
That's one of them.
Um, I'm not sure.
All right, looking at this right here, positive direction is down the ramp, that's this right here. Negative direction is up the ramp, so I've got friction here, but I also have
Tension? Tension?
yes. And that equals,
Mass 1 acceleration?
there we go. All right, two more equations to go. I think at this point, everyone, oh, Madison, I don't think I've heard your voice in terms of one of these equations, have I?
Mm.
Well, I randomly pick you. So we're doing the mass 2 over here.
Okay. So would that be W2 sine theta 2?
You're doing the I-hat.
Yeah. Would it be FT minus?
Because up the ramp is positive. So that's the positive one. Okay?
And then would be so would that just be M2A?
Okay. And one equation to go. Let's just open it up.
W2 cosine theta 2 minus, I can't see what that is, I hat?
What's that? That's a Y.
Oh. Sorry, Y2. Down 0.
And again, technically, mass 2 times 0, but that's still 0. All right. So we have our two equations, or sorry, two. Some people call it 4. We have our 4 equations here. Friction is involved. So since it's friction 1, I know Y1 will be involved. Y2 actually is irrelevant right now. So we need to figure out, is it going to exceed, are we going to go over the breaking point for static friction? I suspect we are, but let's go ahead and figure it out. So we do our substitution. So this first one becomes M1G sine theta 1 minus mu SY1 minus tension is equal to M1A. The second equation, Y1 is equal to M1G cosine theta 1. The next one, tension minus M2G sine theta 2 equals M2A. And then M2G cosine theta 2 is equal to Y2. Again, that fourth equation we aren't going to use here. It's just there as arm candy for the rest of the equations. All right, so to solve it, I'm gonna take this, plug that in for Y1. And then I'm gonna add the two equations at the same time. So I'm gonna put that in there, I'm gonna add the two equations, get rid of my FTs. That's why I have M1G sine theta 1 minus mu S M1G cosine theta 1 minus M2G sine theta 2 equals M1A plus M2A. And very similar to before, my acceleration therefore would be M1G sine theta 1 minus mu s M1G cosine theta 1 minus M2G sine theta 2 divided by M1 plus M2. In essence, this is still force divided by mass. I have M1G sine theta 1 trying to move the whole system in the direction we know it wants to go. And then I have two things holding it back. I have friction, and I have the component of the weight of mass 2 trying to pull it back. So now we plug and chug. And that was 6 times 9.8 times the sine of 57 degrees minus 0.1 times 6 times 9.8 times the cosine of 57 degrees minus 8 times 9.8 times the sine of 30 degrees divided by 14. Well, I know this right here is 39.2. And I know this right here, 39.2. And this was that's 1/2. We just did this, like etched in the dirt somewhere there. Not so much for my memory.
Yeah.
That was good.
Is that 38 degrees?
30 degrees.
Oh, my bad.
It was 39.2?
Yeah.
Okay. The other one was 49.3? And then the new part.
3.20.
3.26?
0.
3.20.
Yes.
All right, so what we do is we end up, this is gonna be a positive number up top. Which means what?
It moves. It accelerates.
Yep. And therefore, what do we do?
Find the acceleration.
All right, we'll get a positive number here, we don't, but once we recognize that our acceleration is positive, what's the next step?
Set friction to equal kinetic friction.
Yeah. So once we recognize it is going to slide, kinetic becomes dominant, and we change that to a 0.5, because that's the one place where the static shows up, is that 0.1, because that was the coefficient of static friction. So this now becomes 1.6. Now we find the acceleration is Kano desperately wanted to do, and so that was 10.1 minus 1.6, then 8.5 over 14.
.607 meters per second squared.
And all's right with the world. questions to hear? For those of you who felt really uncomfortable when I called on you, I do appreciate you're still playing along. I'm hesitant to do that just because of a student years ago who broke down in tears. I thank you for not breaking down in tears. But if you needed to, I would hope you would feel free to do it. It's like family. I had the alarm set so that I, one, wouldn't forget, and also to hand stuff back. So, you know, you are welcome. Ian. I don't know what order these are in anymore. James? By the way, after I did this, I did a quick check to see what grades people could make in the end, assuming I correctly predict the number of labs, quizzes, tests, and so forth. Everyone in here is still in that. You will not, none of you can do better than an A, and none of you can do worse than an F. So, grades I'm handing back is narrated down that much.
Thank you.
Yep.
Thank you.
And I probably stop this before I flash a grade.